Today, we're diving into a really radical idea. What if the universe isn't this smooth, flowing river we've always imagined? What if it's more like a computer running on a grid? It's a totally new rulebook for reality that asks a simple but profound question. It's not just what the best state of a system is, but how the universe can physically even build it in the first place.
So let's just start with the core problem here. When a physicist talks about finding the best state of a quantum system, what they really mean is the most stable one, right? The one with the lowest possible energy. But, and this is key, it has to obey a whole set of rules. We call this constrained optimization. It's kind of like how your GPS finds the fastest route to your destination without just telling you to drive through a building. It has constraints. And physicists think the universe does something very similar to settle into its preferred state.
To really get a feel for this, let's use an analogy. Imagine you're standing in front of a massive mountain range. That range represents every single possible state a system could be in. Your job is to find the absolute lowest valley. Simple, right? Well, there's a catch. You can't just wander around wherever you want. You have to stay on one very specific hiking trail. That trail is your constraint. So how do you find the lowest possible point while staying on that trail? That's the exact puzzle we're talking about.
Okay, so to really appreciate how big a deal this new idea is, we have to first look at the old way of doing things, the classical approach that's been the foundation of quantum mechanics for like a century. You can think of it as this beautiful, perfect, smooth map of that mountain range we just talked about.
Now, this classical map has a name, Hilbert space. And it's a purely mathematical world. It's not physical, it's abstract, and in this space, every possible quantum state is just a single point. But the most important assumption, the one that everything else rests on, is that this landscape is perfectly smooth and continuous. There are no gaps, no pixels, no individual steps. It's just a flawless, infinite continuum of possibilities. And in this beautifully smooth, continuous world, finding the answer is incredibly elegant. You use a mathematical trick called Lagrange multipliers, and it all just boils down to solving a single equation. You find one point where all the forces, the energy pushing you down and the constraints holding you on the path, are in perfect balance. It's one critical point in a purely abstract space, and boom, you have your answer.
But here's where the Gibsonian framework comes in with a major critique. It says this classical method is ontologically external. That's a fancy way of saying it describes the what without ever explaining the how. It's like having a perfect blueprint for a supercar. The blueprint tells you the top speed, the horsepower, but it tells you absolutely nothing about the engine, the gears, the pistons, the actual parts that make it work. It finds a mathematical answer, but it never asks if reality can physically build or support that answer.
And that, right there, brings us to the new paradigm. What if we've been using the wrong kind of map all along? The Gibsonian framework says, hey, let's stop thinking of reality as a smooth landscape and start imagining it as a discrete, computational grid. Seriously, think of it more like the world inside a video game.
And this slide just lays it out perfectly, right? The two worldviews side by side. The classical view is all about that smooth, continuous reality. The Gibsonian view throws that out and says, no, reality is fundamentally discrete. It's built on a lattice, a grid, where things happen in distinct locations and in distinct steps, a lot like pixels on a screen.
And here's the absolute kicker. This isn't just a clever analogy. The discreteness, this grid, it isn't just some useful approximation we use for our computer models. The Gibsonian framework is making a much bigger claim. It's saying this grid is the ontological base layer. It's the fundamental hardware that our universe actually runs on.
So if reality really does operate on a grid, well, you can't use the old rulebook. It just doesn't apply anymore. You need a completely new set of rules, a whole new kind of physics and math to go with it. So let's take a look at the Gibsonian rulebook.
First things first, you need a new language, a new kind of math. So instead of the smooth, flowing curves of traditional calculus, this framework uses something called we-field calculus. The best way to think about it is, it's less like calculating the smooth flow of water in a river and more like counting individual water drops as they fall into a grid of ice cube trays. It's a math built for a world of discrete tokens and figuring out how they pile up in specific spots.
Okay, and get this. A quantum state is no longer just a simple point on a map. In this new view, it's a rich, multi-channel object. It has all these internal properties. Imagine that instead of just being a location, it's a complex little machine sitting at that location with its own internal stresses and structural supports. These hidden properties, things like internal stability and cohesion, they turn out to be absolutely crucial for deciding whether that state can even exist.
Which brings us to probably the single most important new rule of them all, the full complement rule. Here's how it works. For a state to even exist at a specific spot on the grid, it needs physical support. It has to receive a full complement of energy and information tokens from its neighbors. If it doesn't get that local support, it literally doesn't matter if it's the most perfect mathematical solution in the world. The universe just can't build it. It becomes what's called an algebraic ghost, a phantom that looks good on paper but can't exist in our physical reality. And this is just one of the new hurdles a state has to clear.
So, with all these new rules in play, finding the best state is no longer about solving one elegant equation. No, now it's about passing a really tough test. Any potential solution has to meet 5 separate conditions to prove that it's more than just an abstract answer, that it is a physically real and stable thing.
That's right, 5 conditions, not one. And here's the tough part, they all have to be met at the exact same time. This makes the whole process so much more demanding because it's specifically designed to weed out all those algebraic ghosts and only keep the states that the universe's hardware can actually build and sustain over time. So here they are, the 5 bouncers at the door of reality. The first 3 are basically the new grid-based versions of the old rules. The solution has to be optimal, it has to follow the constraints, and its probabilities have to add up correctly. But the last 2, these are the real game changers. Number 4, full complement admissibility. That's the physical support rule we just talked about. Can its neighbors actually build it? And number 5, multi-channel stability. Means the state has to be internally sound. You know, all those hidden properties, they can't have any critical flaws, like being under too much internal stress. Only a state that gets a green checkmark on all 5 of these can truly exist.
This table really just sums up the whole story perfectly. With the traditional method, a solution is an abstract point in space that solves a math problem. In the Gibsonian framework, a solution is a stable, physical object on a grid that has to pass 5 tough physical tests. It's the huge difference between an abstract, algebraic critical point and a truly physically realizable state.
So, okay, let's zoom out. What are the bigger implications of all this? If this framework is even close to being on the right track, it completely reframes how we think about physics itself.
What it's suggesting is that finding the best state, optimization, isn't just some calculation that we do on a blackboard. It's a physical process, something that's literally baked into the hardware lock logic of the universe itself. It's like reality is constantly running these checks in the background, making sure states are physically supported and internally stable before they're ever allowed to pop into existence.
So, at the end of the day, why does this matter? Well, for one, it creates a direct bridge between our abstract equations and what is physically possible in the real world. It makes us see quantum states not as points, but as rich objects with hidden support structures holding them up. And maybe, most profoundly, it takes optimization from being just a tool for physicists and promotes it to being a core process of the universe's own fundamental operating system.
And I love this quote because it's so insightful. It's saying the old answers we found aren't necessarily wrong. They're just incomplete. The classical solution is like a shadow of the true, much richer Gibsonian state. Think about it. A 2D shadow gives you some information about a 3D object, right? But you lose an entire dimension of detail in the process. That's what's happening here. The old method gives us a flat projection of reality, but misses all the physical depth.
Which leaves us with this final massive question. This framework paints a picture of a universe that acts like a computer, one that operates with very strict, very physical hardware rules about what can and cannot exist. So if that's true, what does that imply about the fundamental nature of our reality? It's a thought that really challenges the very foundation of everything we thought we knew about the cosmos.